So we looked at how this system kind of changes and how the rate of change dH by dt is going to change depending on where we position this. But we need to then, how do we how do we apply related rates to this problem? Okay, so we want to go back to the steps that we had. So first thing we need to do is relate the variables involved to each other in a calculation. So I have my y position, I have my x position, I have the distance between, which is my hypotenuse. So it follows a Pythagorean relationship. So the relationship I'm going to use to connect this all is x squared plus y squared equals the h squared. Okay. So once I've done that, I want to differentiate this with respect to time. And by doing that, I'm going to generate my dy by dt's, my dx by dt's, and my dh by dt's. So I have to be careful when I'm doing this because I'm going to differentiate this implicitly. So I'm going to first start with the x squared. So I'm going to differentiate x squared into 2x. But because x is an embedded function, okay, x is a function of time, I have to apply the chain rule and add in the times dx by dt. Plus, then I move on to the y squared. I'm going to differentiate y squared, so I get 2y. But again, y changes with time, so it's a function of time. So I have to apply the chain rule and differentiate dy by dt. Equals. I do the same thing with my h. I'm going to differentiate h squared to 2h. And because h is a function of time, I need to multiply by the chain rule, dh by dt. So now I've generated all the parts that I need. So let's check. Do I have the different parts? Do I have x? Well, yeah, I've been given x as 50 meters. Check. My dx by dt I've been given here as negative 10 meters per second. My y, yeah, I've been given y. The y position is 40 meters, so I have that. My dy by dt, I have that as well, as negative 5 meters per second. My h, well, I have h here, but I don't have the value of h. However, because I know the position of y and x, I can just use Pythagoras and calculate the value of h. So if it's 40 meters vertically and 50 meters horizontally, I just use Pythagoras. So I'm going to do 4 squared plus 5 squared is 41, square root 41, and because it's 10 times bigger, I'm just going to multiply that by 10. So I get 10 root 41. Okay, so basically we're just going to use Pythagoras to work out that value. You can work out the decimal value if you like. However, it's probably nicer to use these exact values. So do I have h? Yeah, I have h now. Okay, I have the value of h. Okay, so that means that I have h here. So I have all the parts of this expression that I need to be able to solve for dH by dt. So then I'm just going to then plug it in. So I get 2 times x. Well, I worked out x is 50. Dx by dt, I know is negative 10 meters per second. Plus 2 times y, the value of y we've been given here is 40, so I'm just going to plug that in. That's 40 meters. Dy by dt is negative 5 meters per second, so I'm going to put negative 5 into here, equals 2 times h. Well, I can replace h with 10 root 41. Okay, and then the only thing left to solve for then is my dH by dt. So then I'm just going to simplify all this. So I get 2 times 50 times negative 10, that's negative 1,000, plus 2 times 40 is 80 times negative 5 is negative 400. This becomes 20 root 41 times dH by dt, and then I can just solve algebraically for dH by dt. So negative 1400 is equal to 20 root 41 times dH by dt. So solving for dH by dt, I get negative, this is going to divide into, I get negative 70 over root 41. And this works out to be, when I calculate this value, it's going to work out to be, looks like, let me just see here on my calculator. On my calculator, I get 10.93, or negative 10.93, and that's going to be meters per second. Okay, so then that, if we actually go back to that animation, that looks like that was our initial position that we have right now, and that was giving us the same value.